Welcome back and welcome in. Settle into whatever soft place you have chosen for tonight. Let your shoulders drop. Let your breath slow. We are going to drift, very gently, toward one of the strangest objects in the known universe. Not a galaxy, not a black hole, not a swirling young world still glowing with the heat of its making. Tonight, we are going to a kind of star that is also, in a sense, a single, enormous atom, a city of matter packed so tightly that one small spoonful of it would outweigh a mountain on Earth. Imagine, for a moment, that you are floating far above our galaxy. Below you, the Milky Way turns slowly, a soft pinwheel of pale light. Among its many billions of stars, a few 100 million are quiet, dark, and small. So small, you could lay one across a single city. And yet, each of these tiny things contains more mass than our sun. They are called neutron stars. They are the cooling hearts of suns that died long ago. We are going to spend the next few hours wondering about what lives inside them, not what we know for certain, because the honest answer is that no one knows for certain. We are going to sit with the open question of what matter becomes when you crush it past every limit we understand. We will visit ideas and theories. We will let them rest beside each other without choosing between them, one small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. Now, let your mind ease back to the image of that neutron star. Picture a sphere about 20 kilometers wide, roughly the size of a quiet town. Its surface is smoother than glass, smoother than anything human hands have ever made. The tallest hill on a neutron star, if it has hills at all, may rise only a few millimeters above the rest. Its color, in our imagination, might be a faint warm glow, fading slowly through the eons, like an ember in the dark. Now feel the weight of it. A single sugar cube of neutron star material, brought here to your bedside, would weigh as much as every human being on Earth combined. That is not a poetic flourish. That is what the numbers say. The matter inside these stars is squeezed so tightly that the empty space inside atoms has been pushed out. The particles that once danced at a polite distance now press against each other directly. The result is a kind of substance we cannot make in any laboratory. We can only study it from far away, by the light and the ripples it sends across the cosmos. And here is where the wondering begins. Out near the surface, we have a reasonable picture, a thin crust of iron and lighter elements, arranged in a crystal lattice, swimming in a sea of free electrons. Below that crust, the picture begins to soften. Neutrons appear in greater numbers, then more, then deeper still. Something happens that we do not fully understand. The pressure climbs past anything our equations were built to describe. The matter may twist itself into long strands and flat sheets, shapes that some researchers have nicknamed nuclear pasta, or it may dissolve into something even stranger, a soup of quarks, the smallest known building blocks, freed from the particles that usually contain them. Some theories suggest that the very center holds free quarks roaming in a hot, dense fluid. Other theories say the core stays made of neutrons all the way down, just more and more tightly packed. A third idea proposes a kind of matter we have never seen anywhere else, called strange quark matter, which would change the rules entirely. The honest truth is that we do not know which picture, if any, is correct. We may be looking at one kind of object. We may be looking at several kinds wearing the same outer shell. For tonight, you do not have to choose. You only have to wonder. Picture that small dark sphere out there in the galactic quiet, spinning, holding its impossible secret, a spoonful heavier than a mountain. A heart we have never seen and may never see directly. As you breathe in, imagine yourself drifting closer to it across the long dark. As you breathe out, imagine the silence around it, deep and ancient and patient. We have a long, slow journey ahead. There is no hurry at all. Before we wander any deeper into the question of what hides inside a neutron star, let us pause and picture the thing itself. Imagine a star much larger than our sun. Picture it burning steadily for millions of years, fusing lighter elements into heavier ones in its hot core. When it finally runs out of fuel, its outer layers blow away in a vast explosion we call a supernova. What remains at the center is something small, dense, and very strange. That remnant is the neutron star, and in the simplest terms, it is the squeezed, cooling heart of a star that has died. To get a feel for one, picture a city, not a sprawling city, but a small one, perhaps 10 or 12 miles across. That is roughly the diameter of a typical neutron star. You could drive from one side to the other in about 20 minutes on a quiet highway. And yet, inside that small sphere, there is more mass than the entire sun. Sometimes a little less, sometimes a little more, but always packed into a ball no wider than a modest town. Try to hold that idea gently in your mind. A whole star, pressed down to the size of a city. The density that comes from this is hard to picture in everyday terms. If you could scoop up a single sugar cube of neutron star material and somehow bring it to Earth, that little cube would weigh about as much as every human being on the planet, all combined. Some estimates put it at around 1 billion tons for a piece the size of a small spoonful. The number is so large that it stops feeling like a number. It just feels like a wall. These objects are also old, in a slow and patient way. A neutron star can keep its shape and spin for billions of years after it is born. Many of the ones we observe today formed long before our sun even existed. They drift through the galaxy quietly, often unseen, sometimes spinning hundreds of times each second, sometimes turning more slowly, like a lighthouse whose beam sweeps past the Earth at a measured pace. Their composition is where the simple description begins to fray. On the outside, a neutron star has a thin atmosphere, maybe only a few centimeters thick. Beneath that lies a crust made mostly of iron nuclei, locked into a stiff crystal lattice. As you move inward, the matter changes. The familiar atoms get squeezed so hard that electrons are pressed into protons, and what comes out the other side is mostly neutrons, hence the name. Most of the star, by mass, is a sea of neutrons jammed shoulder to shoulder. That much we are fairly confident about. The trouble begins when we try to describe the deepest interior. Once you go below the crust and into the core, the pressure climbs to values we cannot recreate in any laboratory on Earth. Our equations of state, the rules that tell us how matter behaves under pressure, start to disagree with one another. Some predict a thick fluid of neutrons with a few protons mixed in. Others suggest that the neutrons themselves break apart into their building blocks, called quarks, set free in a kind of dense soup. We cannot yet see inside to settle the question. For now, treat the neutron star simply as this: a dead star's remnant, a city-sized sphere holding the mass of the sun, a surface of iron, a body of neutrons, and a hidden center whose true nature is still up for debate. The nearest known neutron star sits a few hundred light years from Earth, which means the light we see from it tonight left its surface centuries ago. Many more drift much farther away, scattered through the disk of our galaxy. Astronomers estimate that the Milky Way may hold around 100 million of them, though most are quiet and hard to detect. They do not shine the way ordinary stars do. Instead, they glow faintly in X-rays, or pulse in radio waves, or send out gentle thermal light as they slowly cool. When you hear the phrase neutron star, then hold these images together. A city you could cross in an afternoon. A weight greater than any star you can see with the naked eye. An age older than the sun. A surface harder than any metal we know. And a core whose true makeup remains one of the open questions of modern physics. We will sit with that core gently in the sections that follow. There is no hurry. The neutron stars themselves are in no hurry either. They have been waiting quietly for a very long time. To understand what hides inside a neutron star, we have to travel back to the moment one was born. And that birth is not gentle. It begins inside a massive star, perhaps 8 or 20 times heavier than our sun, near the end of its long life. For millions of years, the star has been burning. It fuses light elements into heavier ones, layer upon layer, like the rings inside an old tree. At the very center, deep beneath the outer shells of hydrogen and helium, the star slowly builds a core of iron. Iron is a quiet ending. It cannot be fused into heavier elements to release more energy. Every other fuel the star has ever used gave back warmth and outward push. Iron does not. And so the iron core grows, silent and patient, while the rest of the star keeps shining as if nothing is wrong. Then comes the moment of failure, when that iron core grows past a certain mass. Around 1.5 times the mass of our sun, it can no longer hold itself up. The pressure inside is enormous, but the iron has nothing left to give. In less than a second, the core collapses inward. A region once the size of the Earth shrinks down to something closer to the size of a city. The fall is so fast that the outer layers of the star do not even know yet that the floor has dropped away beneath them. What happens next is one of the most violent and beautiful events in the universe. The infalling matter is squeezed so tightly that electrons and protons are forced together. They merge into neutrons, releasing a flood of tiny particles called neutrinos. These neutrinos are nearly massless, almost ghostly. They pass through ordinary matter without leaving a trace. And yet, in this brief moment, so many of them are released at once that they carry away most of the energy of the dying star. The collapse stops suddenly when the new neutron core becomes too stiff to crush any further. The infalling outer layers bounce off this hard new heart. A shock wave begins to climb back outward, and the neutrinos help drive it. The star tears itself apart in a supernova, scattering its outer atmosphere across light years of space. What gets left behind, sitting quietly in the middle of the expanding glow, is the neutron star. It is still hot at first, astonishingly hot, hundreds of billions of degrees in its interior, but neutrinos pour out of it like steam off a kettle, carrying heat away into the dark. Within minutes, the surface cools to perhaps 1,000,000 degrees. Within thousands of years, the outside is cooler still, though the inside stays warm for far longer. As it cools, something curious happens at its outer edge. A crust begins to form. This is where iron returns to the story. The outer crust of a neutron star is thought to be a lattice of atomic nuclei, with iron and other heavy elements packed in a tight crystal arrangement. Free electrons drift between them like a calm sea. It is, in a strange way, the most familiar layer of an object that is otherwise unlike anything else in nature. The crust is only about 1 kilometer thick, perhaps less. Beneath it, the world becomes truly alien. Yet even at the surface, theories diverge. Some models suggest the very top might hold a thin atmosphere of hydrogen or helium, only centimeters deep. Others wonder whether carbon dominates instead, or whether the surface chemistry shifts as the star ages. The crust itself may be smooth in places and cracked in others. The exact arrangement of nuclei, the precise mix of elements, even the temperature at which the crust solidified, all of these remain open questions that researchers are still working through with careful models and limited observations. And below this iron shell, the story grows stranger still. The pressure climbs. The familiar rules of chemistry begin to break down. Nuclei swell with extra neutrons that would never be stable on Earth. The boundary between one nucleus and the next blurs. Somewhere in that deepening pressure, matter stops behaving like anything we have ever held in a laboratory. But that is a layer for later. For now, picture the newborn neutron star, cooling in the silent dark, wrapped in its quiet shell of iron and exotic isotopes. The supernova that made it has already faded into a soft glow against the stars. The neutrinos have long since fled. What remains is a small, dense world whose very surface is built from the ashes of a star that no longer exists. And beneath that surface, deeper than light can reach, the real mystery is only beginning. Beneath the iron shell of a neutron star, the world changes in ways that stretch the very meaning of matter. The crust we spoke of before sits like a thin floor above an ocean, and that ocean is unlike any sea on Earth. It is made almost entirely of neutrons, trillions upon trillions of them, packed together so tightly that the rules we learned in chemistry class begin to fall away. To picture this, imagine reaching down through the surface, past the lattice of iron and heavier nuclei, and entering a region where atoms themselves cannot hold their shape. The pressure here is so great that electrons are squeezed into protons, and the two merge into neutrons. This process has a quiet name. Physicists call it neutronization. It is the slow, crushing transformation of ordinary matter into something stranger. The neutrons that form this sea were once part of every kind of atom you can name: carbon, oxygen, silicon, iron, all of it broken down and remade. And those original elements, in turn, were forged inside earlier stars long before the neutron star itself was born. The iron in the crust above came from the same kind of stellar furnace that seeded the iron in Earth's core. The oxygen that once made up water molecules in some ancient world may now exist here, pressed into a form it could never take on a planet. This is one of the quiet wonders of the universe. The matter inside a neutron star is not foreign. It is recycled. Every neutron in that vast inner sea once belonged to something familiar. A grain of dust, a patch of ice on a passing comet, a breath of gas in a stellar nursery, and now, gathered by gravity into a single small sphere, all of it has been reduced to its barest essentials. Just below the iron crust, in a region called the inner crust, something extraordinary begins to happen. The neutrons start to leak out of the nuclei. They drift between the heavier atoms like water seeping through gravel. Researchers call this a neutron drip. It marks the boundary where matter stops behaving like a solid and starts behaving like a strange new fluid, layered inside a solid frame. Deeper still, the structure of the nuclei themselves begins to bend and stretch under the pressure. The familiar round shapes of atomic nuclei flatten into sheets. They twist into tubes. They braid into shapes that physicists have named after pasta: spaghetti, lasagna, gnocchi. This is nuclear pasta, and it is thought to be one of the strongest materials in the known universe. But here we must be careful. Nuclear pasta has never been directly observed. It exists in computer simulations and in theory, and most researchers believe it must be there. The exact shapes and how they behave remain a genuinely open question. Beneath the pasta layer lies the outer core, where almost everything dissolves into a smooth fluid of neutrons, with a small fraction of protons, electrons, and even heavier particles called muons drifting through. The proportions are delicate. The fluid sits in what physicists call beta equilibrium, a balanced state where particles are constantly turning into one another at matched rates. It is a quiet dance, hidden from any telescope, taking place under conditions no laboratory on Earth can ever recreate. And this is where the mystery deepens. We can describe the outer crust with reasonable confidence. We can model the inner crust and the nuclear pasta with decent care. But once we cross into the deep core, our equations begin to disagree with one another. Some models say the matter remains a fluid of neutrons all the way down. Other models suggest the neutrons themselves may break apart, releasing the quarks inside them into a kind of free soup. Both ideas remain on the table. Both have supporters, neither has been confirmed. What makes this so difficult is that we cannot reach in and take a sample. We cannot send a probe. The only messengers we have are the faint signals that escape. Pulses of radio light, X-rays, and the ripples of gravitational waves from distant collisions. From these whispers, we try to reconstruct an entire hidden interior. It is worth pausing on the scale of this. The matter inside a neutron star contains atoms that may once have drifted through ancient nebulae, planets that no longer exist, oceans on worlds we will never see. All of it now lies compressed into a sphere only a few miles wide. The same particles, a different state, still part of the same long story the universe has been telling itself for billions of quiet years. To understand what may be happening inside a neutron star, we have to think about the forces at war within it. Forces that push, forces that pull, forces that squeeze, and forces that hold the line. Each of them is working at scales we never meet in daily life. And somewhere in the middle of that quiet battle, in the deepest part of the core, the answer to one of the great mysteries of physics is hiding. Start with gravity. Gravity is the great squeezer here. A neutron star packs more mass than our sun into a sphere only about 20 kilometers wide. That kind of compression bends space itself. If you could stand on the surface, you would weigh billions of times more than you do now. The pull is so strong that light leaving the surface loses energy as it climbs away. Gravity wants to crush the whole star down into a single point, the way it crushes the matter inside a black hole. But something stops it. Something pushes back. That something is called degeneracy pressure, and it comes from a strange rule of the quantum world. Tiny particles, like neutrons, do not like to share the same state. When you pack them too close, they resist. They push outward, not because they are hot, but because the rules of quantum mechanics simply forbid them from getting any closer. This pressure is what holds a neutron star up. It is a stalemate. Gravity squeezes. The quantum world refuses to budge. Now picture that balance, deep inside, where the densities climb past anything we can recreate in any lab on Earth. This is where the mystery lives. The forces involved are no longer just gravity and quantum pressure. The strong nuclear force, the same force that binds protons and neutrons together inside ordinary atoms, becomes the main player. At the core of a neutron star, the strong force is being pushed harder than it has ever been pushed anywhere else in the known universe, and we do not fully understand how it behaves under those conditions. One idea is that the neutrons stay neutrons all the way down. The core is just a denser, hotter version of the layers above. Another idea is that the neutrons cannot survive the squeeze. They break open. The quarks inside them, the smaller pieces that make up every proton and neutron, may come loose and swim freely. This is called quark deconfinement, and it would mean the very center of the star is not made of particles we would recognize. It would be a soup of quarks and the gluons that bind them, a phase of matter that exists nowhere else. A third possibility goes further still. Some researchers wonder whether a strange flavor of quark matter, made partly of so-called strange quarks, could be more stable than ordinary matter under that kind of pressure. If that is true, the core might be made of something exotic, something with rules of its own, or the whole star might be, from surface to center. Each of these theories fits some of the evidence. None of them fits all of it. Heat plays a quieter role in all this. A young neutron star is born blistering hot, hundreds of billions of degrees in the moment of its birth, but it cools quickly, shedding energy through tiny particles called neutrinos that slip out of the star almost unnoticed. Within a million years, it may settle to a steadier glow. The way it cools, fast or slow, can tell us something about what is hiding inside. Different core materials cool at different rates. Astronomers watch these temperatures over the years, looking for clues. Magnetic fields add another layer. The fields wrapped around a neutron star are the strongest in the universe, trillions of times stronger than the field of our planet. They twist the crust, channel the radiation that escapes, and may even reach down into the deeper layers and shape how the matter flows. How those fields are generated and how they survive for so long remains an open question of its own. So, picture the neutron star as a place where four great forces meet at once. Gravity pulling everything down, quantum pressure pushing it back up, the strong nuclear force trying to hold particles together while they are squeezed past their limits, and magnetic forces threading through all of it, silent and immense. The balance between them sculpts the star over millions and even billions of years. And at the very center, where those forces reach their most extreme expression, we still do not know what kind of matter answers them. The core keeps its secret. We can only listen for hints from the outside and wonder what shape they are pointing toward. Let us sit for a while with the sheer scale of what we are talking about, because numbers alone slide off the mind. A neutron star is the size of a small city. The one above your imagination tonight is perhaps 12 miles across, top to bottom. You could walk its diameter in an afternoon, if walking were possible, on a surface where you would weigh as much as a mountain range. Inside that small sphere lives more mass than the sun. Pause on that for a moment. Our sun is a ball of plasma so wide that 1,000,000 Earths could fit inside it. Now, squeeze all of that, and a little more, into a space the size of a quiet town. The density becomes something the human body has no way to feel or picture. A single sugar cube of neutron star matter would weigh about 1 billion tons here on Earth. That is roughly the mass of every car in the United States, packed into a space smaller than your thumbnail. To picture how tight that packing is, imagine the atoms in your hand. In ordinary matter, atoms are mostly empty space. If the nucleus of a single atom were the size of a marble, the nearest electron would be circling several city blocks away. Almost everything you touch, including your own skin, is mostly nothing at all. Now imagine that gravity squeezes all the empty space out. The electrons are crushed into the protons. The nuclei are forced together until they touch, and then until they smear into one another. What is left is matter packed as tightly as the nucleus of an atom itself, stretched across a sphere the size of a mountain. Somewhere beneath that surface, in the layer we call the outer core, We believe the matter behaves as a fluid, not a fluid like water. Something far stranger. A sea made mostly of neutrons, with a smaller swirl of protons mixed in and a thin scatter of electrons and muons threading through it all. The protons may be only 5 or 10% of the mix, but they matter enormously. They carry charge. They couple to magnetic fields. They may even, according to one well-supported idea, flow without any resistance at all. That idea is called superconductivity, and on Earth, we only see it in carefully cooled laboratories near absolute zero. Inside a neutron star, the temperatures are millions of degrees, and yet the pressures are so vast that the protons may pair up and slip past one another with no friction. If the theory holds, somewhere beneath the crust there is an ocean of protons that flows like a perfect liquid, carrying electric currents that never fade. Some researchers think this superconducting sea is what shapes the star's enormous magnetic fields. Others wonder whether the picture is more complicated, with regions where the protons remain ordinary, and regions where they pair up, the two phases sitting side by side in ways we cannot yet map from the outside. Try to feel the scale of this. A teaspoon of the outer core would, if you could somehow lift it free, weigh more than every human being who has ever lived combined. The pressure inside that teaspoon is greater than the pressure at the center of any planet, greater than the pressure at the center of any ordinary star. And in this crushing place, a strange calm reigns. The neutron fluid may itself be a superfluid, a state in which the neutrons flow without any internal friction whatsoever. If you stirred such a fluid, the swirl would never slow down. It would simply keep turning, quietly, for the lifetime of the universe. We cannot send a probe to confirm any of this. The matter would tear apart any instrument long before it reached the surface. So everything we believe about that proton ocean comes from indirect clues. The cooling rates of neutron stars over decades, the tiny hiccups in their rotation, the shape of the light they release. From these whispers, we build our models. Some models say the proton fluid takes up most of the outer core. Some say it is a thinner layer than we thought. Some say the very idea of separate proton and neutron fluids breaks down at the deepest densities, where everything becomes something else entirely. For tonight, hold the picture gently, a city-sized sphere, a weight beyond comprehension, and somewhere within it, possibly, a silent sea of protons gliding past one another, without resistance, carrying invisible currents through a place no eye will ever see. The scale is almost too much to hold, so let it rest in the back of your mind, where wandering happens on its own, and the body begins to soften toward sleep. Imagine, for a moment, that you could drift down toward the surface of a neutron star, not land on it. Nothing made of ordinary atoms could survive that, but float just close enough to see. What rises beneath you is unlike any world you have ever pictured. The surface is smooth in a way nothing on Earth is smooth, smoother than glass, smoother than still water. The whole sphere is a polished ball only about 20 kilometers across, and yet it holds more mass than our sun. The color, if you could see it with your eyes, would shift depending on the star's age and temperature. A young neutron star, fresh from its violent birth, glows a pale, searing white. Its surface burns at temperatures of around 1,000,000 degrees, radiating mostly in X-rays we cannot see with naked eyes. If our vision could stretch into that range, the star would look like a tiny welding arc, painfully bright, holding steady against the deep black behind it. As the star ages over millions of years, that glow softens. Older neutron stars cool to a deep sullen red, almost ember-like, fading slowly toward darkness. The terrain itself is the strangest part. There are no continents, no oceans, no clouds, just a thin, crystalline shell of iron and lighter elements, packed into a lattice so tight that the spaces between atoms have nearly vanished. Picture a single, unbroken sheet of frozen metal wrapped perfectly around the entire star. The crust does not shimmer or flow. It simply sits, impossibly rigid, under gravity so strong that any bump taller than a few millimeters gets pulled flat almost at once. The tallest mountain on a neutron star might rise only as high as a grain of rice, and yet, in proportion to the star itself, that grain of rice holds the strain of a continental peak. Now here is where the mystery begins to gather beneath your feet. The crust you are looking at is only a thin skin, perhaps a kilometer deep on a star 20 kilometers across. Below it, the matter changes, and deeper still, near the very center, something happens that physicists genuinely do not understand. One leading idea is that the pressure becomes so extreme that the neutrons themselves break apart. Inside every neutron sit 3 smaller particles called quarks, bound together by the strong force under normal conditions. Quarks are never seen alone. They are always locked inside larger particles, hidden away. But in the heart of a neutron star, some researchers wonder whether that lock finally breaks. If it does, the core might be filled with what physicists call quark matter, a soup of free-roaming quarks, no longer trapped inside neutrons, flowing as a kind of liquid that exists nowhere else in the known universe. This is the puzzle of quark matter. We can write equations that describe it. We can run simulations on the largest computers. But we cannot reach inside a neutron star and look. We can only observe the outside and try to guess what the inside must be. A competing view holds that quarks never quite escape. In this picture, the core stays made of neutrons and protons all the way down, just packed tighter and tighter, perhaps forming exotic shapes we have not yet imagined. Other researchers suggest something in between, a gradual blending, where the line between neutron and quark blurs across many kilometers of depth. Each of these ideas predicts a slightly different size for the star, a slightly different stiffness, a slightly different way it would ring if it were ever struck. So far, our measurements cannot quite tell them apart. Floating above that polished surface, you would have no way to know which theory is true. The outside looks the same in every case, a smooth, glowing ball, silent in the dark. The mystery hides beneath the skin, sealed away by gravity that would crush any probe long before it reached the answer. There is something quietly humbling about this. The matter inside a neutron star may be the densest, stable form of matter in the cosmos, denser than anything we will ever create in a laboratory, and the question of what it actually is, what shape it takes, what rules it follows, remains genuinely open. The surface gives nothing away. It just glows and cools and waits. As you drift here in your imagination, let the strangeness settle in slowly. A smooth glass sphere the size of a small city, weighing more than a star, hiding a secret no telescope has yet pulled into the light. We will keep looking. For now, the puzzle stays just beneath that perfect, silent skin. Picture, if you can, a sphere about the width of a small city. Now picture that sphere turning, not slowly like a planet through a long day, faster than seems reasonable for something made of matter. Some neutron stars complete a full rotation in less than 1/100th of a second. The fastest ones we have found spin more than 700 times each second. A point on the surface of such a star moves at a fair fraction of the speed of light. Sit with that for a moment as you rest. A ball of crushed atoms, heavier than the sun, whirling like a hummingbird's wing. And yet from the outside, in the dark hush of space, it makes no sound. It only sweeps its narrow beams of light across the galaxy, tick by silent tick, like the slow second hand of a vast and patient clock. The mystery deepens when we ask why some neutron stars spin so fast. The ones born in supernovae start fast already, because they inherit the spin of a much larger collapsing core. When a star, bigger than the sun, shrinks down to the size of a city, its rotation speeds up the same way a skater pulls in her arms. But that alone does not explain the fastest cases. Those stars, called millisecond pulsars, seem to have been spun up later, after their birth, by stealing matter from a nearby companion. The infalling material would have struck them at an angle, like rain pushing a water wheel, slowly winding them up over millions of years. That story fits the evidence well, but the details remain open. We do not fully understand how much spin a neutron star can hold before it begins to break apart, or before its own gravitational waves carry that spin away. There is a theoretical limit, sometimes called the breakup frequency, beyond which the surface would simply fly off into space. The fastest pulsars we have found sit comfortably below that limit, but no one is sure why. Some researchers wonder if there is a softer ceiling, an unseen break, that stops these stars before they reach the cliff edge. Others suspect that tiny bumps in the crust radiate gravitational waves and steady the spin. Both ideas are still being tested. And then there is the question of what such a fast rotation does to the interior. Imagine the deep core, packed with neutrons and perhaps stranger things, being stirred and shaped by that constant whirl. The star is not a rigid ball. Its inside may behave like a fluid, or several fluids layered together, each one rotating at slightly different speeds. The crust spins as a single solid piece, but beneath it, the neutron sea may be turning a little faster or a little slower, in patient disagreement with the shell above. We cannot see this directly. We can only infer it from the way the spin sometimes wobbles or skips. One striking idea is that the inner regions hold a superfluid, a strange state of matter that flows without any friction at all. If true, this superfluid would spin not as a smooth hole, but in countless tiny whirlpools called vortices, each one carrying a fixed share of the rotation. The vortices would pin themselves to the crust, and when they suddenly slip free, the star would lurch. That lurch may be what we observe as a glitch, a small but measurable jump in the pulsar spin rate. Other researchers argue that glitches could arise from the crust itself cracking and rearranging, without any need for a superfluid at all. Both pictures fit some of the data. Neither fully explains all of it. What lies even deeper, in the very heart of the spin, is harder still to imagine. If the core holds free quarks, those quarks too would be carried along in the rotation. They might form their own currents, their own patterns of flow, governed by rules we are still working out. A spinning neutron star, in this view, would be a layered engine of fluids and lattices, each level moving to its own quiet rhythm, all locked together by gravity into one steady beacon. It is humbling to think that something so violent in its motion appears from far away as a calm and regular pulse. The light reaches us as a soft, repeating whisper, while inside, the matter races at speeds that strain our understanding. We can measure the outside. We can time the pulses to a millionth of a second. The interior, with its possible vortices and quark currents and pinned superfluids, remains a closed room, with the door only slightly ajar. The whisper continues, and we keep listening, hoping to learn the shape of the dance within. every neutron star spins, and every neutron star carries a magnetic field. These two cycles are wound together so tightly that we still cannot fully untangle them. The field of an average neutron star can be 1 trillion times stronger than the magnetic field of the Earth. In the strangest cases, called magnetars, the field grows 1,000 times stronger still. We have measured these fields. We can see their effects in radio beams and in flares of soft gamma rays. What we cannot do, even now, is fully explain how they came to be. The puzzle begins with the parent star. A massive star, before it collapses, has a magnetic field of its own. When the core falls inward and shrinks from something the size of a small planet to something the size of a city, the field lines are pulled in with it. This compression alone can amplify the field by an enormous factor. Squeeze a magnetic field into a smaller volume, and its strength rises sharply. For ordinary neutron stars, this fossil field from the parent star may be enough to account for what we see. The magnetism is, in this view, an inheritance frozen into the new crust as it cools. The trouble is that magnetars do not fit this picture cleanly. Their fields are so intense that simple compression of the parent star's field cannot easily reach those values. Something else must happen during or just after the collapse. One leading idea is the dynamo theory. In the first seconds after the supernova, the newborn neutron star is a roiling, churning fluid. It spins rapidly. It convects violently. If the spin and the convection couple in the right way, they could act like a vast generator, winding the magnetic field tighter and tighter, until it reaches the staggering values we observe in magnetars. A competing idea holds that the fossil field is enough on its own, so long as the original star happened to have an unusually strong field to begin with. In that picture, magnetars are simply the descendants of stars that were already deeply magnetized. Both ideas have evidence in their favor. Neither has settled the question. These fields are not static. They evolve over millions of years in slow, quiet cycles that we are only beginning to map. Inside the crust, currents of charged particles drift and decay. As they decay, the magnetic field weakens. The decay is uneven. In some regions it speeds up, in others it slows down. Over very long time scales, the field may rearrange itself, twisting and reconnecting in slow, silent adjustments. A young neutron star with a powerful field will gradually become an older neutron star with a gentler one. The pulse of its radio beam, the heat of its surface, the way it spins down, all of these are tied to the slow erosion of magnetism over geological spans of time. Magnetars give us a more dramatic kind of cycle. Their fields are so strong that they actually stress the crust from beneath. The field lines press outward. The rigid crust resists. Pressure builds. Then, in a moment, the crust shifts, the field reconnects, and a flash of energy erupts from the surface. We see these as soft gamma repeaters and as giant flares. Some of these flares carry more energy in a fraction of a second than the sun releases in 100,000 years. The cycles between flares can stretch from days to decades. They are not perfectly periodic. They feel more like the slow, irregular breathing of a stressed material that finally gives way. What remains genuinely unknown is the geometry inside. We see the field outside the star, where it shapes the beam and the wind. We can only guess at how it winds through the deep interior. Some models picture a simple dipole, like a bar magnet, threading from pole to pole. Others suggest a much more tangled topology, a knot of toroidal loops trapped beneath the crust, holding far more energy than the outer field reveals. If those hidden loops exist, They may quietly power the surface activity for millions of years. They may also influence the deeper layers, perhaps even the strange phases of matter near the core. The interior magnetic field could be one of the keys to the central mystery of what neutron star matter truly is. For now, we watch the pulses arrive. We listen to the steady drum of a young pulsar and the occasional bright cough of a magnetar. The rhythms tell us something. They do not tell us everything. The cycles of these magnetic giants continue, mostly hidden, mostly silent, beating slowly through the dark. A pulsar, left to itself, behaves like a very patient clock. It spins, and with each turn it loses a tiny sliver of its energy to the magnetic field that wraps around it. Over thousands of years, the spin slows down in a smooth, predictable way. Astronomers can measure that slow decline with astonishing precision. The pulses arrive on time, and on time, and on time again, like soft footsteps in a quiet hallway. Then, sometimes, the clock stumbles. Without warning, the star suddenly spins a little faster. The change is small. The pulse rate shifts by perhaps 1 part in a million, sometimes less. Yet for an object as steady as a pulsar, this tiny jump is a shout in a silent room. These sudden speed-ups are called glitches, and they have been seen in dozens of pulsars over the past 50 years. Each one is a small puzzle, and together they form one of the gentlest mysteries in all of astronomy. What could make a star skip ahead in its own rotation? The leading idea points inward to a hidden neighbor living inside the star itself, deep in the interior. Researchers suspect there is a superfluid, a strange liquid of neutrons that flows with no friction at all. A superfluid does not slow down the way ordinary matter does. While the solid crust above it loses speed over the centuries, the superfluid inside keeps spinning at its old, faster rate. The two layers drift apart, like two dancers slowly falling out of step. For a long time, nothing happens. The faster inner sea and the slower outer shell coexist, separated by a delicate boundary. Then, in an instant, the boundary gives way. The superfluid shares some of its extra spin with the crust, and the whole star speeds up just a touch. That, at least, is one picture. It is a beautiful one, and it fits much of what we see, but it is not the only picture, and the details remain open. A competing idea looks at the crust itself, not the fluid beneath it. In this view, the crust is under enormous strain as the star slows. Eventually, the strain finds release in a kind of small rearrangement, a settling of the rigid outer shell. The radius of the star shrinks by the tiniest amount, and a spinning object that shrinks must spin faster, just as a skater pulling in her arms turns more quickly. Some glitches may come from the fluid, others may come from the crust. Many may come from both at once, with the two effects feeding into each other in ways we cannot yet untangle. Glitches are interesting not only for what they are, but for what they hint at. They suggest that the interior of a neutron star is not one smooth thing, but a layered world with neighbors that interact. There is a solid crust, and beneath it a sea of free neutrons, and beneath that, something stranger still. Each layer has its own behavior, its own way of moving, and its own way of speaking to the layer above. A glitch is a brief conversation between these neighbors, overheard from many light years away. Some pulsars glitch often, others glitch rarely, or never at all in the time we have watched them. A few favorite stars in the southern sky have given astronomers dozens of glitches to study, each one a little different from the last. The size of the jump, the time it takes the star to settle back down, the way the pulse shape changes in the days after, All of these carry quiet clues about the inner sea. By matching the patterns to different models of the deep interior, researchers hope to learn how much of the star is superfluid, how thick the crust is, and how the layers are bound together. So far, the clues do not all agree. Some glitches recover quickly, others take months to fade. Some pulsars seem to be storing up energy for a future jump, while others release it in small, frequent pulses. The equations that describe these neighbors inside the star are still being written and rewritten as new observations come in. For tonight, it is enough to picture the steady tick of a faraway pulsar, somewhere in the Milky Way, sending its pulses across the dark inside that small, dense star. Two neighbors are quietly drifting apart, one made of solid lattice, the other of frictionless fluid. They have been doing this for a long time. Soon, perhaps, they will speak to each other again. The star will skip the smallest fraction of a beat, and someone on Earth, watching very carefully, will notice. The rest of us will simply rest. On a neutron star, the word mountain means something very different. Picture the surface beneath you, a polished plane of iron and lighter elements, packed so tightly that a sugar cube of it would outweigh a fleet of ships. Now imagine a wrinkle in that plane, a small ridge pushing up from the crust. On Earth, a mountain might rise 5 or 6 miles into the sky. On a neutron star, the tallest possible peak may only stand a few millimeters tall, the thickness of a fingernail, the height of a grain of rice. And yet, in the strange physics of these objects, that tiny bump is a true mountain. The reason is gravity. The pull at a neutron star's surface is roughly 200 billion times stronger than what you feel right now. Sitting or lying in your quiet room, anything that tries to rise above the smooth crust must fight against that crushing weight. The crust itself, though, is incredibly strong. It is the strongest material we know of in the universe, perhaps 10 billion times stronger than steel. So it can hold up a little ridge, a small lump, a faint wrinkle in its surface. As long as that wrinkle stays very, very small, how tall a neutron star mountain can actually be is still an open question. Older estimates suggested ridges of a few centimeters might be possible. More recent work, using better models of the crust, has pulled that ceiling down to roughly a millimeter, maybe less. Some researchers wonder if certain neutron stars, with unusual histories or unusual interiors, might support slightly larger features. Others argue the smooth, quiet crust would never allow it. The answer matters because even a tiny bump on a spinning neutron star should send out gravitational waves, faint ripples in space that detectors here on Earth might one day catch. So far, no such steady ripple has been heard. That silence tells us something. It tells us neutron stars are smoother than we once imagined. Their crusts have somehow settled into shapes that are nearly perfect spheres, with only the gentlest of imperfections. The question of what shapes are possible and how they form sits in the back of every theorist's mind. There are other extremes here, stacked on top of one another like layers in a strange and silent cake. A neutron star can spin hundreds of times every second. The fastest known pulsar turns about 716 times each second, its equator moving at roughly a quarter the speed of light. Try to picture an object the size of a small city, more massive than the sun, whirling that fast without flying apart. The crust holds. The shape barely changes. The mountains, if there are any, stay buried at the millimeter scale. The temperatures are extreme in both directions. A newborn neutron star can begin its life at over 1 trillion degrees inside, hotter than anything else in the present universe. Within minutes, it cools to a few billion. Within thousands of years, the surface drops to perhaps 1,000,000 degrees, glowing faintly in X-rays. Old neutron stars, drifting alone in the dark for billions of years, may cool down to surfaces of only a few 100,000 degrees, almost shy by their standards. The magnetic fields can reach beyond imagination. A typical neutron star carries a field about 1,000,000,000,000 times stronger than Earth's. A Magnetar, a rarer cousin, can reach 1,000 times stronger still. Inside such a field, atoms cannot hold their normal shapes. Electrons stretch into thin tubes along the field lines. Chemistry, as we know it, simply stops working. Whether these enormous fields come from the parent star or are generated by churning fluids inside the newborn neutron star is still debated. There are good arguments for both ideas, and the truth may involve a little of each. And then there is the density. The deepest interior may reach values 5 to 10 times the density of an atomic nucleus. Our equations begin to lose their footing there. We can guess what the matter is doing, but our guesses depend on which theory we trust. Nuclear pasta, free quarks, strange matter, something stranger still. The mountains, the spins, the temperatures, the fields, the densities. Every measurement pushes against the limits of what we thought matter could endure. And yet the star sits there, calm and small, no larger across than a quiet coastal town, holding all of this inside itself. The records are extreme. The interior remains hidden, and somewhere on that polished surface, a ridge no taller than a grain of sand may be sending the faintest whisper out into the dark, waiting for us to hear. Far out in the dark, in places too quiet for any ear to reach, the surface of a neutron star sometimes trembles. The shaking is small, so small that, on Earth, we would need our most sensitive instruments to notice anything at all. Yet, for a star whose crust is harder than steel, and packed beyond imagining, even the faintest shiver carries meaning. These tiny tremors are called starquakes, and they are one of the most beautiful, least talked about details in all of stellar science. A neutron star spins. As it spins, its shape is not perfectly round. The rotation pulls it just slightly outward at the equator, giving it the gentlest bulge. Over thousands or millions of years, that spin slows down. And as it slows, the bulge wants to ease. The crust, though, is stiff. It resists the change. Stress builds quietly within the lattice, the way ice on a frozen lake builds pressure as the seasons turn. Then, in a moment too brief to measure with old instruments, the crust shifts. A piece of it cracks, settles, and the star adjusts its shape by perhaps a fraction of a millimeter. That fraction of a millimeter, on a star so dense, is enormous in its own way. Some researchers think these tiny shifts are linked to the small spin glitches we sometimes see in pulsars. Others believe the glitches come mostly from the superfluid interior, with the crust playing only a small role. Both ideas may be partly right. The honest answer is that we do not yet know which contribution matters more, and the picture probably changes from one star to the next. What scientists find lovely about starquakes is their scale. A neutron star might be only 20 kilometers across, smaller than many cities. Its tallest possible mountain, by current theory, may rise no more than a few millimeters from the surface. So when a starquake happens, it is reshaping a world where the highest peaks are the size of a grain of rice. Imagine, for a moment, a perfectly smooth sphere, the size of a small town, polished to a shine, where the only landscape is a faint roughness you could not see with your eyes. That is the canvas, and on that canvas, the quakes write their slow, patient signatures. The crust itself is a wonder of texture. In its upper layers, atomic nuclei sit in a tight lattice like tiles in a vast mosaic, with a sea of free electrons drifting between them. Deeper down, the nuclei grow stranger, swollen with extra neutrons. Deeper still, they may stretch and flatten into the shapes researchers playfully call nuclear pasta. When a starquake occurs, these layers shift against one another in ways no laboratory on Earth can fully recreate. Some theorists wonder if the cracking happens mostly in the brittle outer shell. Others suspect the pasta layers, with their odd geometries, may be where the real motion takes place. The question stays open. There are subtler details still. After a large starquake, a neutron star can briefly glow more brightly in certain wavelengths of light, or release a soft burst of energy. The crust may oscillate, ringing like a struck bell, with vibrations that fade over seconds or minutes. From those rings, researchers try to read the interior, the way someone might guess the contents of a sealed jar by tapping it. The notes they hear are faint, and the translation is incomplete. We can pick out a few frequencies. We are not yet sure what each one is telling us. Most starquakes happen in silence, in the sense that no human will ever directly witness them. The stars where they occur are often thousands of light years away. By the time any signal reaches us, the quake itself is long past, and the surface has long since stilled. We are reading old, faint letters from a place that does not know we are listening. There is something tender about that. The star adjusts itself, almost imperceptibly, in the slow rhythm of its cooling life, and across the gulf of space we catch a single quiet word. These small details rarely make their way into the loud stories told about neutron stars, the mergers, the gamma bursts, the magnetar flares. Those get most of the attention. The everyday tremor, the millimeter scale settling of a crust, the gentle ringing of a star no bigger than a city, lives mostly in scientific papers and patient minds. Yet it is in these tiny motions that some of the deepest secrets of the interior may eventually be read. For now, the star trembles softly in the dark, and we listen, and we wonder what the trembling is trying to say. For centuries, the idea of a neutron star did not exist. The very particle at its heart, the neutron, was not even discovered until the year 1932. So the story of how we came to know these strange, dense bodies is also the story of a young science, one that had to invent its tools and its language almost from scratch. In the early 1930s, two astronomers working in California began to wonder what might happen when a massive star ran out of fuel. Their names were Walter Bardet and Fritz Zwicky. Looking at the brightest stellar explosions in the sky, the ones we now call supernovae, they proposed something bold. The outer layers of the dying star, they said, blow away in light and fire. But the core does not vanish. It collapses inward until its protons and electrons are crushed together, leaving behind a tiny sphere made almost entirely of neutrons. They wrote this idea down in a short paper in 1934. At the time, most of their colleagues thought it was a curious guess, and little more. For 3 decades, the neutron star remained a theory on paper. No one knew how to find one. The objects were predicted to be only about 20 kilometers across, smaller than many cities. From across light years, they would be far too faint to see with any telescope of the era. The idea drifted along in the background of physics, waiting for an instrument that could listen instead of look. That instrument was radio. After the Second World War, astronomers began building large radio dishes to study the hiss and crackle of the sky in long wavelengths. In 1967, at a field outside Cambridge in England, a graduate student named Jocelyn Bell Burnell was scanning printouts from a new radio array. She was hunting for the twinkle of distant quasars. Instead, she noticed a small smudge of signal that did not behave like anything she had seen before. It came from the same patch of sky every night, and when she looked more closely, the signal was not a steady hum. It was a pulse, a clean, sharp tick, repeating every 1.337 seconds, as regular as a clock. At first, no one knew what to make of it. The signal was so precise that some half joked it might be a beacon from another civilization. The team labeled the source LGM, one short for Little Green Men, as a placeholder. But within months, more pulsing sources appeared, in different parts of the sky, at different rates. Whatever was making them, it was natural, and it was common. The explanation came together quickly once the theorists looked at the numbers. A pulse this fast and this sharp had to come from something very small and spinning very rapidly. A normal star is too large to spin that quickly. A white dwarf, the remnant left by smaller stars, would tear itself apart at such speeds. Only a neutron star, just a few kilometers across, could rotate that fast and hold together under its own gravity. The old idea from Bardi and Zwicky, sitting quietly for 33 years, suddenly had its evidence. What was reaching the radio dishes was not the whole star, but a beam of radio waves sweeping out from its magnetic poles. As the neutron star spun, the beam swept across Earth like the light from a lighthouse. Each pass made a pulse. Astronomers gave these objects a new name. They called them pulsars. In the years that followed, the catalogue grew quickly. Pulsars were found embedded in the glowing wreckage of past supernova explosions, exactly where theory had predicted. One sits at the heart of the Crab Nebula, the remains of a star whose explosion was recorded by Chinese astronomers in the year 1054. That nebula had been studied for centuries before anyone realized a tiny spinning corpse was buried in its center, sending out a pulse 30 times each second. Each new pulsar deepened the puzzle. The signals were steady enough to rival atomic clocks, yet they came from objects formed in the most violent events in the cosmos. The light reaching us carried hints of conditions we could not reproduce in any laboratory on Earth. What lay beneath that thin radio whisper was a world of densities and forces that the equations of the time could only describe in rough sketches. We had finally seen the neutron star, in a sense, but we had only seen its outermost breadth. The interior, the strange and crushing depths where matter does whatever matter does at the edge of possibility, remained as hidden as it had ever been. The pulse told us something was there. It did not tell us what. Among the family of neutron stars, a small group stands apart in a way that still puzzles those who study them. We call them magnetars. They are neutron stars too, born from the same kind of collapse, made of the same crushed matter. Yet they carry magnetic fields so strong that the numbers feel almost unreal. A typical neutron star already holds a field 1 trillion times stronger than the magnet on your refrigerator. A magnetar can carry a field 1,000 times stronger than that. To picture what this means, imagine bringing a magnetar within the distance of the moon. Long before it arrived, its field would erase every credit card on Earth. It would pull iron from the blood of living things. It would warp the shape of atoms themselves, stretching them into thin needles aligned with the magnetic lines. At close range, matter as we know it would stop behaving like matter. Chemistry would no longer work. The familiar rules would quietly bend. What we cannot yet explain is how such fields come to exist at all. One leading idea is the dynamo theory. In this picture, the newborn neutron star spins very quickly in the moments after the supernova. Hot, churning fluid Inside the star twists and amplifies a starting field, like a hand stirring cream into coffee, until the field grows monstrous. If the spin is fast enough and the convection vigorous enough, an ordinary neutron star becomes a magnetar. But there is a competing view. Some researchers wonder whether the strong field is inherited, not built. The massive star that collapsed may have already held a powerful field, locked into its core long before the supernova. When the core fell inward, the field lines were squeezed into a tiny volume, and what we see today is simply the fossil of that earlier magnetism. Both stories can explain some of what we observe. Neither story explains all of it. The question remains open. The strangeness does not end with the fields. Magnetars sometimes release sudden bursts of light, brief flares of gamma rays that arrive without warning and then fade. The largest of these, the so-called giant flares, can outshine for a fraction of a second every other source of high-energy light in the galaxy. The current best guess is that the crust of the magnetar cracks under the strain of the twisting field beneath it. When the crust shifts, the field snaps into a new shape, and a pulse of energy escapes. Some studies favor this Starquake picture. Others suggest the trigger lies deeper, in instabilities within the field itself, with the crust playing only a small role. Both ideas are still being tested. What makes magnetars genuinely surprising is how they connect to the deeper mystery of what lies inside a neutron star at all. The strength of the field may shape the matter beneath it. Where the field is extreme, the pressure and the structure of the inner layers may differ from those in a quieter neutron star. Some models suggest that very strong fields could change the way nuclear pasta forms in the inner crust, stretching or aligning those strange shapes along the magnetic lines. If that is true, then no two neutron stars are quite alike on the inside. The field, the spin, the history of birth, each may leave its own fingerprint in the dense interior. Whether this is correct, or whether the inside settles into the same arrangement regardless of the field, remains unresolved. There is also the puzzle of how long a magnetar stays a magnetar. The fields are so strong that they should drain energy over time, slowing the star and weakening the field. Within perhaps 10,000 years, the magnetar phase should end. Yet, we keep finding objects that seem older than this and still carry strong fields. Either the fields decay more slowly than we think, or magnetars are being born, more often than the simple counting suggests. Or something else is keeping the fields alive. No one is sure. A magnetar is, in many ways, a neutron star pushed to its limit. It takes the already impossible density of its kind and adds to it a magnetism that bends the rules of matter further still. It hints that the interior of these stars is not a single, simple state, but a place shaped by forces we are still learning to describe. Tonight, as you settle, picture a small, dark sphere only a dozen miles across, wrapped in invisible lines of force so strong they twist the empty space around them. Quiet on the outside, restless within. We do not yet understand it. A neutron star does not sit alone in the dark. It cools, it loses heat to the empty space around it, slowly, over millions and billions of years. And the way it cools turns out to be one of the gentlest, most patient clues we have about what hides inside. Think of a freshly forged neutron star, just minutes old. It begins at temperatures so high that the numbers stop meaning much to our ordinary minds. Hundreds of billions of degrees. Then, within seconds, it shrugs off most of that heat in a flood of tiny particles called neutrinos. Neutrinos are ghostly little messengers that barely interact with anything. They slip out through the star like smoke through a screen door, carrying energy away into the void. After that first wild moment, The cooling slows. The star settles into a long, quiet life. And here is where it begins to whisper to us about its interior. The rate at which a neutron star cools depends, in a deep way, on what its core is made of. If the core is a calm fluid of neutrons, protons and electrons in balance, the cooling follows one curve. If the core hides exotic matter, free quarks perhaps, or strange particles called hyperons, the cooling follows a different curve, faster in many cases. So, when astronomers measure the surface temperatures of neutron stars of different ages, they are, in a sense, listening for the music of the interior through the heat that escapes. The trouble is, the music is faint, and our ears are still learning. One neutron star, in particular, has held the attention of researchers for decades. It sits at the heart of a supernova remnant called Cassiopeia A, the leftover glow of a stellar explosion whose light reached Earth a few centuries ago. The star is young, by cosmic standards, and some observations suggest it has been cooling unusually quickly over recent years. One leading idea is that we are catching it in the act of a phase change deep inside. Neutrons in its core pairing up into what physicists call a superfluid state, where the fluid flows without any friction at all. If that idea is right, it would be a beautiful confirmation that the strange quantum behavior we see in laboratories on Earth also plays out in the crushing pressures of a stellar corpse. But not everyone is convinced. Other researchers argue that the apparent cooling could be an instrument effect, or a slower change misread over too short a window of time. The data are precious and few. The star will outlast the argument. This is the symphony of it, though the cooling of a neutron star is not a story about the star alone. It is a story about how the smallest particles we know, neutrinos, quarks, neutrons in quantum pairs, connect to the largest scales we can observe. The same neutrinos that drain heat from a neutron star are the ones streaming through your body right now from the sun. Trillions of them every second, passing through your skin and bones as if you were not there. The sun sheds them. Supernovae shed them in titanic bursts, and old neutron stars, deep in their slow retirement, sigh them out into the galaxy. The crust plays its part as well. Heat rises from the core through the inner crust, where the nuclear pasta may live, and then through the outer crust of crystalline iron until it finally reaches the thin atmosphere and glows away as a faint X-ray shimmer. Each layer slows the heat differently, so the temperature we measure at the surface is shaped by every region between us and the center. The whole star is involved. Every phase, every fluid, every lattice contributes its voice to the final note. What remains unknown is whether the cooling curves we have gathered so far truly point to one universal recipe for neutron star interiors, or whether different stars hide different cores. Some may carry quark matter, some may not. Some may have superfluid layers that begin at one depth, others at another. The equations that describe matter at these densities still disagree with one another, and the observations are not yet sharp enough to choose between them. For now, astronomers gather temperatures from old neutron stars scattered across the galaxy, plotting them against age, looking for patterns. It is patient work, more like tending a garden than chasing a storm. And the star, at the heart of Cassiopeia A, whatever it is doing, will keep on cooling whether we watch or not. Its heat will fade into the dark. Its secrets will leak out, slowly in the form of light too faint to feel, and we will keep listening. Nothing in the universe truly holds still. Even neutron stars, those small, heavy remnants of dead suns, do not sit alone forever. Some of them are born in pairs. Two massive stars, locked in orbit, can both reach the end of their lives and collapse, leaving behind 2 neutron stars, circling each other in a slow, silent dance. For most of their lives, that dance is quiet. The 2 stars trace gentle loops around their shared center, the way 2 skaters might glide around each other on a wide pond of ice. But the dance never lasts. Across millions, sometimes billions of years, the 2 stars draw a little closer with every orbit. They give up a tiny piece of their motion to space itself. That lost motion travels outward as ripples in the fabric of space-time. Gravitational waves, the slow exhale of the cosmos as massive bodies move. Each ripple is invisible. Each one is gentle beyond imagining. And yet, drop by drop, they carry the orbit's energy away. A pair might begin its long descent separated by millions of kilometers. Over time, that gap shrinks, the orbit tightens, the 2 stars circle faster. They were already turning quickly when they formed, but as the centuries pile up, the dance becomes a true blur. Near the end, in the final seconds of an spiral that has lasted longer than the age of mountains, the 2 neutron stars whip around each other hundreds of times per second. The ripples they pour into space become a rising tone, a chirp that grows higher and louder until the 2 bodies finally meet. What happens in those last moments is something we are only beginning to understand. 2 objects, each more dense than anything else in the visible universe, slam together at a meaningful fraction of the speed of light. The matter inside them, already squeezed past the limits of our equations, is squeezed further still. Some theories suggest the merger briefly forms a heavier neutron star that wobbles and rings before either settling down or collapsing into a black hole. Other theories suggest that, depending on how stiff or soft the inside of a neutron star really is, the collapse to a black hole can happen almost at once. We do not yet know which picture is closer to the truth, and the answer depends on the very mystery this episode keeps returning to. What matter does at the core? This is where the slow change becomes a sudden one. For ages, the 2 stars drifted closer with the patience of geology. Then, in less than a heartbeat, they remake each other. The crusts shatter. The interiors mingle. Whatever exotic state lived at the deepest center of each star. Neutron fluid, nuclear pasta, free quarks, or something we have not yet named, meets its counterpart in the other star. For a brief window, conditions exist that cannot exist anywhere else, not even in our most powerful machines on Earth. The gravitational waves that escape these final moments carry information about the interior in a way that ordinary light cannot. When the 2 stars are very close, each one stretches the other slightly. How easily they stretch depends on what they are made of. A softer interior would deform more. A stiffer interior would resist. That subtle stretching changes the rhythm of the gravitational wave chirp. By listening carefully to that rhythm, researchers can begin to constrain what kind of matter sits at the heart of a neutron star. The first such event, detected in 2017, already nudged the theories, narrowing the range of possibilities. Future detections may narrow them further, but the answer is not yet in hand. Mergers also remind us that neutron stars are not unchanging monuments. Even when isolated, a neutron star is slowly transforming. Its spin gradually slows as it sheds magnetic energy. Its interior cools across millions of years. Its crust may fracture and resettle, and if it has a partner, its orbit shrinks century by century until the long spiral ends in a flash. The neutron star you see in any given snapshot is just one frame in a story that began with a supernova and may end with a collision. There is something quietly humbling about this. 2 of the strangest objects in the universe, hidden inside their own gravity, sometimes find each other and combine. They write their final chapter in a language of ripples we have only recently learned to hear, and in those ripples may be the answer to a question we have asked for decades. For now, we listen. The pairs are out there, drifting closer, in no hurry at all. When two neutron stars finally meet, after their long, slow spiral through the dark, the universe lights up in a way that nothing else in nature can match. For a brief moment, the small patch of space where they collide becomes one of the brightest places in the cosmos, and in that light, woven through the searing glow, are the heavy metals that will one day rest in a wedding band, in a wire, in a coin pressed between fingers. Gold, platinum, uranium, born in the meeting of two dead stars. This is one of the gentlest surprises in modern astronomy. For a long time, no one was quite sure where the heaviest elements came from. Stars can fuse light atoms into heavier ones, but only up to a point. Iron is the wall. Past iron, fusion stops giving energy and starts taking it. So where did the gold come from? Where did silver and lead and the rare earths come from? Some came from supernovae, the explosions of dying giant stars, but the math never quite added up. There was always too much heavy metal in the galaxy, and not enough supernovae to explain it. Then, in 2017, telescopes around the world watched two neutron stars merge. The signal arrived first as a ripple in space-time itself, a faint gravitational wave passing through Earth. Seconds later, a flash of gamma rays, and in the hours and days that followed, a soft glow appeared in a galaxy more than 100 million light-years away. That glow had a color, and the color told a story. In the first hours, the light was blue, a pale, cool blue, the color of very hot matter, spraying outward at a noticeable fraction of the speed of light. Then, as the days passed, the blue faded, and a deeper red emerged, a slow, dim, ember red, like the last glow of a fire late at night. That shift from blue to red was the fingerprint scientists had been waiting for. It matched what one theory predicted should happen when heavy elements form in the wreckage of a neutron star collision. The process has a name. Researchers call it the R process, short for rapid neutron capture. In the chaos of the merger, a thick fog of free neutrons surrounds the debris. Atomic nuclei drift through this fog and swallow neutrons faster than they can shed them. They bloat into heavier and heavier forms, climbing the periodic table in seconds. Then, as the fog thins, these unstable atoms decay into the stable heavy elements we recognize: gold, platinum, the pale shimmer of palladium, the dull weight of lead. The light we see is the slow afterglow of that decay, radioactive atoms cooling, settling, releasing their last bit of energy as warmth and color. Astronomers gave this kind of glow its own name. They call it a kilonova because it shines about 1,000 times brighter than an ordinary nova, yet far dimmer than a supernova. A middle kind of brightness, quiet and brief, lasting only a week or two before fading into the dark. But the question is not fully settled. Some researchers believe most heavy elements are made this way, in the rare meeting of two neutron stars. Others wonder whether certain kinds of supernovae, the ones that spin very fast and carry strong magnetic fields, might also forge their share of gold. The single merger we watched in 2017 fit one set of models well, but a single event is not a full census. To know how much of the universe's gold comes from neutron star collisions, and how much from other sources, astronomers will need to watch many more mergers and study the colors of each glow. there is also a quieter mystery folded into the light. The exact shade of red, the exact rate of fading, depends on what the inside of a neutron star is really made of. If the cores hold soft, squishy matter, the merger spreads more debris and the glow looks one way. If the cores are stiff, holding firm against the crush, less material escapes and the glow looks slightly different. So the color of the kilonova carries a hidden message about the unseen heart of the star. Researchers are still learning to read it. For tonight, it is enough to imagine two ancient cinders drifting closer over 100 million years, a final embrace lasting less than a heartbeat, a spray of matter so hot it shines blue and cools to red, then fades to nothing, and scattered through the dark, the soft seeds of every gold ring, every platinum thread that anyone has ever held, made in a place no one will ever visit, by a light no one was meant to see. Space is often called silent, and in the strict sense it is. Sound needs a medium to travel through, and the empty stretches between stars are far too thin to carry waves the way our atmosphere does. Yet matter still vibrates. Neutron stars hum and ring in ways we cannot hear directly, but can sometimes measure. When scientists shift these vibrations into the range of human hearing, the universe begins to whisper back. And no, is that whisper stranger than at the edge, where a neutron star ends and a black hole begins? There is a threshold, somewhere in the mass scale of dead stars, where matter can no longer hold itself up. Below that line, gravity loses its battle with a strange pressure inside a neutron star, and the object stays a star. Above that line, gravity wins. The matter collapses past every known barrier, and a black hole forms. But we do not know exactly where that line sits. We do not know what the heaviest possible neutron star looks like, or what it sounds like in its final moments before the surrender. When two neutron stars spiral together, the last seconds of their dance are filled with a rising tone. Gravitational wave detectors on Earth have caught this signal more than once. The frequency climbs as the stars draw closer, and when researchers convert that signal into audio, it sounds like a soft chirp, a slow ascending note that ends in a sudden silence. The chirp lasts only a fraction of a second in the human range, but inside that brief sound is a record of matter being squeezed harder than anywhere else in the known universe. What happens at the very end of that chirp is one of the deepest puzzles in this field. If the combined mass of the two stars is small enough, a single heavier neutron star may survive. It would spin wildly, wobble and ring like a struck bell for a few seconds before settling. Some theories predict that this ringing carries a high-frequency tone, a kind of aftersong, encoded in further gravitational waves. We have not yet caught one of these post-merger tones clearly. Our detectors are not quite sensitive enough at those frequencies, but future instruments may pick up that song, and if they do, the shape of the tone could reveal what kind of matter sits in the core. If the merged object is too heavy, though, the song ends almost at once. The new star cannot hold itself up. It collapses, and a black hole takes its place. The gravitational wave signal cuts off sharply, like a singer who simply stops mid-note. Somewhere between those two endings, the ringing bell and the sudden silence, lies the true boundary between neutron star and black hole, and we still do not know where that boundary is. One theory suggests the line sits at roughly 2.5 times the mass of our Sun, though the exact value depends on what the interior is made of. If the core holds soft, easily compressed matter, the limit is lower. If the core holds stiff matter that resists crushing, the limit is higher. Some researchers wonder whether a brief in-between object can exist, a hypothetical hypermassive neutron star that survives for milliseconds before collapsing. Others suspect that quark matter forming during the merger could change the song in subtle ways, leaving a fingerprint in the chirp that we have not yet learned to read. There are other sounds too, when we let ourselves stretch the meaning of the word. Pulsars give off radio pulses with steady rhythms, and when researchers play those pulses through speakers, the result is a soft regular tick, sometimes slow and patient, sometimes rapid like a sewing machine. Magnetars, with their sudden flares, would sound like distant thunder if we could ever stand near enough to hear them, though of course we never could. The crust of a neutron star, when it cracks during a starquake, sends out waves that some scientists model as deep bass tones, far below anything a human ear could process without help. All of these sounds are translations, not true sounds. They are the universe's vibrations rendered into something our bodies recognize. And in that translation, we find another version of the same open question. The chirp ends. Does it end in a ringing bell, or in silence, or in something in between we have not yet imagined? The edge between neutron star and black hole may not be a single sharp line at all. It may be a soft blurred region where matter does things our equations cannot yet describe. For now, the sound simply stops, and we are left listening to the quiet that follows. There is a strange beauty to neutron stars that has little to do with what we can see. They are too small and too distant to show us their faces. No telescope will ever bring us a clear picture of their surface. What we have instead is mathematics. And the mathematics, when you sit with it quietly, has a kind of music to it. Begin with a single number. A neutron star holds about 1.5 times the mass of our sun, sometimes a little more, sometimes a little less. That mass is folded into a sphere only about 20 kilometers across. You could drive across one in 20 minutes, if such a drive were possible. From those two simple numbers, density, gravity, and escape velocity all fall out like fruit from a shaken tree. The density works out to something near 400 million tons per cubic centimeter. Near the core, the gravity at the surface is roughly 200 billion times what you feel right now. Light itself bends so sharply around a neutron star that you can see a little of its far side curving into view. The math says this must be true, and observations of pulsar light curves agree. The elegance lies in how few ingredients the equations need: pressure, density, temperature, and a relationship between them. That last relationship is called the equation of state, and it is the heart of every neutron star model. Feed in an equation of state, and the math tells you the star's maximum mass, its radius, how it cools, how it spins, how it deforms. Change the equation of state, and the whole star changes with it. This is where the beauty meets the mystery. We have many possible equations of state, and we do not yet know which one nature uses. Some predict softer interiors, where matter compresses easily and the star stays small. Others predict stiffer interiors, where matter resists compression and the star grows larger for the same mass. The difference between soft and stiff might be only a few kilometers in radius. That tiny gap is where the deepest secrets hide. Astronomers have a clever tool for this. They measure the masses of neutron stars in binary systems by timing their pulses to fractions of a microsecond. Some pulsars have been timed for decades, and their orbits are known with a precision that borders on the absurd. From those orbits, masses fall out cleanly. The discovery of neutron stars heavier than 2 solar masses ruled out many of the softest equations of state in a single stroke. Radius is harder. To pin down a radius, you need to catch X-rays from the surface and model how they bend on their way to us. A space telescope called NICER, mounted on the International Space Station, has been doing exactly this. Its measurements give radii somewhere between roughly 11 and 13 kilometers, depending on the star. The numbers are tightening, but they are not yet tight enough to choose between competing interior models. Then there is the geometry of spin. A neutron star can rotate hundreds of times per second. The fastest known pulsar turns about 716 times in a single second. At its equator, the surface is moving at roughly a quarter the speed of light. The math of rotating relativistic bodies is delicate. The shape flattens slightly. The light from the surface drags along with the spin. Every measurable detail becomes a clue. Even the wobble of a neutron star carries information. A perfectly symmetric, perfectly fluid star would emit no gravitational waves on its own, but the smallest deformation, a bump only a millimeter tall, would send a faint, continuous ripple across the cosmos. Detectors on Earth are listening for those ripples right now. None has been confirmed, which itself is a kind of measurement. It tells us neutron stars are smoother than we once thought. The numbers connect in ways that feel almost too neat. The maximum mass depends on the equation of state. The radius depends on the equation of state. The tidal deformability measured during a merger depends on the equation of state. 3 different observations, 3 different windows, all pointing at the same hidden thing. If the universe is consistent, and we believe it is, then all 3 must agree on a single answer. So far, they almost do. The allowed region of equations of state has shrunk year by year, like a slowly tightening net. Yet, within that shrinking region, several very different pictures of the core still survive. Nuclear pasta, free quarks, strange matter, something stranger still. The math has narrowed the mystery without solving it, which may be the most honest thing mathematics ever does. Inside a neutron star, there is a kind of quiet that nothing on Earth can match. Beneath the crust, beneath the mantle of strange nuclear shapes, beneath even the dense fluid of neutrons and protons, there may be a hidden state of matter that flows without any friction at all. We call it a superfluid, and the idea that a superfluid lives inside a neutron star is one of the most delicate, beautiful, and unproven pictures in all of physics. A superfluid is a liquid that has fallen below a certain temperature and slipped into a strange new behavior. On Earth, we can make helium do this in special labs, cooling it until it climbs the walls of its container and slips through cracks too small for any normal fluid. It flows without losing energy. It does not slow down. If you stirred it, the swirl would keep turning, in principle, forever. Now picture that same behavior, but inside a star. Neutrons in the inner crust and outer core may pair up 2 by 2 into something like couples that dance together. These pairs can glide past one another without resistance. The whole interior may be threaded with a silent, frictionless sea, while the solid crust above turns slowly with the rest of the star. The reason we suspect this comes from those tiny glitches we spoke about earlier. A pulsar slows down over time, very gradually, as it loses energy. But every so often, it speeds up by a hair. Then it settles back. One leading idea is that the superfluid inside is spinning a little faster than the crust, and now and then it transfers some of that spin outward in a sudden pulse. It is as if a hidden ocean inside the star occasionally nudges the shell that surrounds it. This picture depends on a fragile balance. The neutrons must be cold enough by their own scale to pair up. They must be dense enough to interact in just the right way. The temperature, the density, the pressure, the proportions of neutrons and protons, The strength of the strong nuclear force at these extremes, all of these, must fall within narrow windows for a superfluid to exist at all. Change one variable too much, and the pairing breaks. The neutrons would behave as a normal fluid instead, and the glitches would need a different explanation entirely. Some researchers wonder whether the protons in the same region might form their own kind of paired state called a superconductor. In that case, they would carry electric currents without resistance, and the magnetic field of the star would be locked into thin tubes threading through the interior. This idea, too, hangs on a balance. If the protons fail to pair, the magnetic field would behave very differently, and the slow drift of that field over millions of years would tell a different story. There are competing views. Some models suggest the superfluid is patchy, existing in some regions, but not in others. Other models suggest that at the highest densities, deep in the inner core, even the pairing falls apart, and matter takes on a form we have no good name for. A few researchers wonder whether quarks themselves might pair into a colorful superconductor of their own, with properties so unusual that we have only sketched them on paper. None of these pictures has been confirmed. Each one rests on assumptions that could turn out to be wrong. What makes the whole arrangement so striking is how narrow the conditions are. A neutron star sits at the edge of collapsing into a black hole. Its matter sits at the edge of dissolving into free quarks. Its interior sits at the edge of becoming a superfluid, or not. A small change in mass, a small change in composition, and the entire inner structure might tip into a different state. Two neutron stars that look nearly identical from the outside could have very different hearts. We see something similar in our own world. Earth holds liquid water because it sits at just the right distance from the sun, with just the right atmosphere, just the right mass to hold that atmosphere in place. A small shift in any of these would change everything. A neutron star, in its own extreme way, is balanced on a similar knife edge. Only the variables are mass and density and the strange rules of nuclear matter. Whether the heart of a neutron star truly flows without friction, whether the protons truly carry their currents forever, whether the quarks deep below have their own hidden pairings, these remain open. We have hints, we have glitches, we have models that fit more or less. A full picture stays just out of reach, resting quietly in the dark. There is an idea, quietly held by some researchers, that sits a little outside the usual story of neutron stars. It is called the Strange Star Hypothesis, and like the best open questions in science, it asks us to reconsider something we thought we already understood. The usual picture goes like this. A massive star dies, its core collapses. What remains is a tightly packed ball of neutrons, with perhaps some exotic matter at the very center. We call it a neutron star, and the name describes what we expect to find inside. But the strange star idea suggests something different. It proposes that some of these dense remnants may not be neutron stars at all. They may be made of something called strange quark matter, and if that is true, they would be a different kind of object entirely, even if they look almost the same from far away. To understand the idea, we have to think about quarks. Quarks are the tiny particles that make up neutrons and protons. There are several kinds, and physicists call them flavors. The two most common are called up and down, but there is a third, heavier flavor called strange. Under normal conditions, strange quarks do not stick around. They decay quickly into lighter ones inside a neutron star, though conditions are not normal. The pressure is so extreme that quarks may break free from their usual prisons inside neutrons, and once they are free, Some researchers wonder if a mixture of up, down, and strange quarks might actually be more stable than ordinary matter, more stable even than the atoms that make up your hand, this planet, and every star you have ever seen. If that is true, the consequences are remarkable. A small seed of strange quark matter, dropped into a neutron star, could slowly convert the whole star into strange matter. The conversion would spread inward and outward, neutron by neutron, until nothing of the original star remained. What would be left is a strange star, a dense sphere of free quarks, bound together by the strong force in a single, vast structure. This idea was first proposed in the 1970s and refined in the 1980s. It is still alive today, though it remains a minority view. Most physicists lean toward the traditional picture, where neutron stars are mostly neutrons with perhaps a small pocket of exotic matter at the core. But the strange star idea has not been ruled out, and that is where things grow interesting. The trouble is that, from the outside, a strange star and a neutron star can look very much alike. Both are small, both are dense, both spin, both can have magnetic fields and emit pulses of radiation. Telling them apart from light alone is nearly impossible. There are subtle hints, though. A strange star in some models could be slightly smaller than a neutron star of the same mass. Its surface could behave differently. Its cooling pattern over millions of years might leave a different fingerprint, and when two of them collide, the gravitational waves they release could carry a slightly different signature than the waves from two ordinary neutron stars. So far, none of these signatures have been clearly identified. The data we have is consistent with the standard picture, but it is also consistent with the strange star picture. At least for some objects, the window has not closed. There is another twist worth pausing on. If strange quark matter really is more stable than normal matter, then small chunks of it, called strangelets, might drift through space. In theory, if a strangelet ever struck an ordinary neutron star, it could begin the conversion process. Some researchers have wondered if this is rare, common, or impossible. The answer is genuinely unknown. There are also competing ideas that sit between the two. One possibility is that a neutron star might have a normal outer region and a strange quark matter core. These are called hybrid stars, and they offer a kind of middle ground. They are neither fully neutron stars nor fully strange stars, but a mixture of both. Whether hybrid stars exist, whether strange stars exist, or whether the universe simply makes neutron stars and nothing more. These questions are still being asked. What is wonderful about the strange star idea is that it shows how much room remains for surprise. The objects we point our telescopes at every night may be hiding a deeper secret in their cores. They may be familiar. They may be something we have not yet named. The same point of light in the sky could mean very different things, depending on what physics decides to do at densities we cannot reproduce. For now, the strange star idea drifts gently among other possibilities, neither proven nor dismissed, waiting for evidence we have not yet learned how to read. For most of human history, we could only study the universe with light. We gathered photons from stars, from nebulae, from the faint glow of distant galaxies, and from them we pieced together what we know. But neutron stars hide their secrets behind a crust that no light can pierce. Their interiors are sealed away by gravity so strong that nothing we send, no probe, no signal, no clever instrument, will ever reach inside them. For a long time, this seemed like a closed door. Then, very recently in the long story of science, a new kind of listening began. Gravitational waves are ripples in the shape of space itself. When two massive objects spiral together, they stir the fabric of the universe, and those ripples spread outward at the speed of light. In 2017, instruments on Earth caught the gentle stretching and squeezing caused by two neutron stars colliding far away. For the first time, we did not just see a neutron star event. We felt it, in a sense, through the geometry of space. That single event opened a door that had been shut for as long as humans have looked up. As the two stars spiraled inward, each one pulled on the other with enormous tidal force. The way they deformed in those last moments left a faint signature in the wave pattern. From that signature, we learned something about how stiff or how soft the inside of a neutron star really is. A stiffer interior resists squeezing. A softer interior gives way more easily. The measurement is delicate, and the answer is still cloudy, but it is the first true whisper from inside. What might that whisper say in a million years, when our instruments are far more sensitive than the ones we have now? The detectors of the future may sit in space, with arms millions of kilometers long, listening across whole oceans of frequency that we cannot hear today. Each merger they catch will carry a clearer story. We may learn whether neutron star cores are gentle fluids of neutrons, or whether quarks roam free in the deepest regions, or whether strange matter sits at the heart, quietly stable, waiting to be noticed. A billion years from now, if humans or whatever we become are still listening, the catalogue of neutron star mergers may number in the millions. Patterns will emerge that no single event could reveal. Perhaps two different kinds of neutron stars will sort themselves out in the data. Perhaps some will show the soft signature of quark matter at their core, and others the stiffer feel of nuclear pasta all the way down. Or perhaps every neutron star will turn out to follow one universal recipe, and the differences we see today will dissolve into a single quiet truth. The universe itself will be different by then. Our own sun will have swelled into a red giant and shed its outer layers, leaving behind a small white ember. The continents of Earth will have drifted, collided, and broken apart again. Many of the bright stars we know tonight will have burned through their fuel and gone dark, yet new stars will still be forming. New supernovas will still leave behind new neutron stars. The galaxy keeps making them, slowly, patiently, the way an old forest keeps growing new trees long after the first ones have fallen. Some of those distant future neutron stars will eventually find partners and spiral inward, just like the pair we heard in 2017. Their waves will roll across space for hundreds of millions of years before reaching whatever detectors exist then. Each signal will be a small letter mailed across deep time, carrying news about the densest matter in the cosmos. It is possible the central question will still not be settled. Matter at those densities may simply be too far from anything we can recreate in a laboratory. We may always be working at the edge of what equations can describe. One school of thought holds that gravitational waves alone, given enough events, will pin down the true state of neutron star cores. Another view suggests we will need help from other signals, from the cooling of old neutron stars, from the quakes of magnetars, from particle physics experiments not yet imagined. The two paths may converge, or they may not. For tonight, the door is open just a crack. We have heard one clear whisper and a few fainter ones since. The rest of the conversation lies ahead, in instruments not yet built, in mergers that happened long ago, whose ripples are still traveling toward us, quietly carrying the news. Step back now. Let the small details of crust and core soften for a moment and look at the whole picture. A neutron star is one small object in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. And yet, inside that one small object, matter does something it does almost nowhere else. It packs itself so tightly that the rules we know begin to blur. The question of what lies in that core is, in a quiet way, a question about the limits of matter itself. Think about where all of this came from. In the first moments after the universe began, there were no atoms at all, only a hot, glowing soup of the simplest particles. As that soup cooled, the first nuclei formed: hydrogen, helium, a trace of lithium. Nothing heavier. The universe was a soft fog of light gases, drifting in the dark. Every other element you know, carbon, oxygen, iron, gold, had to be built later, inside stars. And so the stars began their long work. They fused hydrogen into helium, helium into carbon, carbon into oxygen, on and on, building heavier elements layer by layer. When the largest stars died, they died in supernovae, scattering their work into space. From those ashes, new stars formed, new planets, new oceans, and eventually, on at least one small rocky world, the atoms gathered themselves into something that could wonder where they came from. You are made of those atoms. The calcium in your bones was forged in a dying star. The iron in your blood was built in the heart of a giant sun that exploded long before our own sun was born. The oxygen you are breathing right now was cooked inside stellar furnaces and flung across the galaxy by the same kind of explosions that leave neutron stars behind. In a quiet, literal way, you are stardust that learned to think. The neutron star is part of that same long story. It is what remains when a great star finishes its work and collapses on itself. The lighter elements drift away into nebulae, where new stars will one day form. But the core stays behind, squeezed into something denser than almost anything else in the cosmos. It sits there, slowly cooling, slowly spinning, holding inside it a state of matter we have never seen anywhere else. This is why the open question matters, even on a sleepy night like this one. When we ask what lies at the heart of a neutron star, we are asking about the deepest behavior of the stuff we are made of. Push protons and neutrons close enough, and they may break apart into their smaller pieces. They may rearrange into shapes we have only sketched on paper. They may form a kind of matter that does not exist in any laboratory on Earth, and perhaps cannot. Each possibility is a hint about the rules that govern everything. The same atoms that built your hands once sat inside an ancient star. The same forces that hold those atoms together, the strong force, the weak force, gravity, electromagnetism, are the forces being tested at the core of every neutron star in the sky tonight. Whatever the answer turns out to be, it will not only describe a strange, distant object, it will describe the limits of the material that makes up worlds, oceans, leaves, lungs, and listeners. There is something gentle in that thought. You are not separate from the cosmos you are wondering about. You are a small, quiet expression of it. The carbon in your skin, the oxygen drifting in and out of your chest, the iron warming your fingertips, all of it came from the same long chain of stellar lives and deaths that produced the neutron stars themselves. In that sense, when we look toward those tiny ancient remnants and ask what they are made of, we are also asking what we are made of. At the very edge of what matter can become, we do not know the answer yet. Maybe nuclear pasta, maybe a fluid of free quarks, maybe strange matter, maybe something stranger still, something no one has thought of, waiting in equations no one has written. The mystery does not need to be solved tonight. It does not need to be solved in our lifetime. It is enough For now, to know that the question is out there, glowing quietly in the dark, woven into the same fabric that makes you. The stars built us, and we, in turn, look back at them and wonder. And so, we come to the end of our long, slow walk through the strangest interiors in the universe. We have stood at the edge of stars that are not quite stars, leaned over crusts of iron, and let our minds sink into seas of neutrons. We have wondered, together, what waits at the core of these tiny, heavy worlds, and we have learned, more than anything, how much remains unknown. Picture, now, a single neutron star somewhere very far away. It spins quietly in the dark, no larger than a small city, yet heavier than the sun. Its surface is smooth and still, polished by gravity into something close to a perfect sphere. Its light is faint. Its motion is steady. It has been spinning this way for millions of years, and it will keep spinning long after this night has passed. Around it, the galaxy turns. Slow arms of stars and dust drift through the deep. Other neutron stars rest in their own quiet corners, each one carrying the same hidden question inside. Some may hold nuclear pasta in their lower crusts, those soft folded shapes of matter we can only describe with mathematics. Some may carry free quarks at their hearts. Some may be stranger still, made of forms of matter we have not yet imagined. We do not know which. We may never know for certain. And that uncertainty, tonight, is not a problem to solve. It is simply a window left open. Think of how small we are, and how patient the universe is with our questions. We send our instruments into orbit. We listen for ripples in space. We measure the pulses of distant beacons and compare them to equations written on chalkboards. The neutron stars do not hurry to answer. They keep their secrets the way a deep ocean keeps its trenches, quietly, without effort, simply by being what they are. Imagine a calm sea on a moonlit night. The waves rise and fall in slow rhythms beneath the surface. In the dark water, there are creatures and currents we have never seen. The sea does not feel mysterious to itself. It only feels that way to us, standing on the shore. A neutron star is something like that. To itself, it is simply matter at rest, doing what matter does when gravity grows strong enough to rewrite the rules. To us, looking up, it is one of the deepest puzzles in the sky. Let your thoughts drift outward for a moment. Picture a quiet planet somewhere in another part of the galaxy, with no one on it, just soft winds moving across pale stone. Above that planet, the same neutron stars shine, faint and steady. The same questions hang in its sky. The universe asks the same riddles everywhere, and answers them in its own slow time. Closer to home, picture our own world turning gently beneath you. Oceans resting, forests breathing, mountains holding their shape against the dark. You are part of this turning, held by gravity to a small warm planet that drifts around an ordinary star. From here, with patient instruments and careful minds, we have learned to feel the tremor of two neutron stars meeting 100 million light years away. That alone is a kind of wonder worth carrying into sleep. The mystery at the center of a neutron star will not be solved tonight. It may not be solved in our lifetimes. Newer detectors will come, sharper measurements will be made. Future minds, perhaps not yet born, may finally read the equation of state that we have been guessing at for decades. Or perhaps the answer will arrive in a form none of us expect, as so many answers in physics have before. For now, the question rests where it has always rested, deep inside small, heavy stars in the dark. There is a kind of peace in unsolved things. They do not demand anything of us. They simply wait, the way the neutron stars wait, slowly spinning, slowly cooling, holding their hidden cores against the pull of time. To wonder about them is enough. To picture them, faint and quiet above a sleeping world, is enough. Let your breathing slow. Let your shoulders soften. Somewhere out there, a neutron star is finishing another rotation, and another, while you settle into rest. The universe is vast, and it is gentle with those who only want to look. You are small, and held, and safe, and the dark is full of beautiful unanswered questions that will still be here tomorrow. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.